Hello, everyone, and welcome into what I fully expect to be the coolest conversation I have here at FreightWaves. I'm your host, Andrew Cox, research analyst here at FreightWaves, and today I am speaking with Sydney Doe, a NASA systems engineer. I want to welcome you, Sydney, and thank you so much for taking the time.
Hi, Andrew. Thanks for having me on today.
All right, Sydney, before we get into your roles at NASA and what you do on a daily basis, tell me a little bit about your story. Where'd you grow up? Where'd you go to school? And how did you end up at NASA?
Sure. So I grew up in Australia, raised in Sydney, Australia, named after my birth city, also hence the accent. Did my undergraduate education there in aerospace engineering. Spent a year in Germany working at a small satellite propulsion company, and then moved to Boston, Massachusetts to do my graduate degrees in aerospace engineering and space systems engineering. From there, I moved to California, where I am currently, to work at NASA's Jet Propulsion Laboratory. It's one of 10 NASA field stations distributed across the country. And since then, I've been supporting the Mars exploration program.
So, Sydney, when we spoke offline, I asked you if NASA was always the goal, or at least was NASA the goal when you were at that German satellite propulsion system? And you said it wasn't the goal then, it was actually the goal when you were a little kid. Tell me a little bit about that.
Yeah, so, I was 6 or 7 years old in Australia, other side of the world, and up on TV comes scenes of astronauts working from the space shuttle, servicing the Hubble Space Telescope with these amazing vistas of Earth in the background, space above it. And then I thought, wow, this is amazing. And shortly thereafter, I learned that humans had walked on the moon. And I thought, this is what I want to do. And so ever since then, I've been working towards finding a career in human space exploration.
Well, you found it. You're at the right place. You're at the foremost experts on space exploration. So, Sydney, let's talk about what you do at NASA. Your roles are kind of mission focused. Tell me a little bit about the couple missions that you are working on right now.
Yeah, so as I mentioned earlier, I've been working for the Mars exploration program ever since joining NASA. NASA's been exploring the surface of Mars continuously since 1997, so that's over 20 years now. And just recently, a few months ago in September, we launched a rover to Mars. It's called the Mars 2020 Perseverance rover. It's more than halfway past its journey on its way to Mars. It will land February 21st next year. And we hope you all join us to watch that amazing event. The mission I've been working on will launch targeting 2026, and its goal is to return rock samples from the surface of Mars for us to study on Earth with the best available instruments and the best available laboratories that we have distributed across the Earth. So if you think about the Apollo program, we returned rocks 50 years ago, and we're still studying them today. We're still learning about the formation of the moon. And we want to do the same with rocks on Mars that have been carefully selected. They'll be carefully selected by the Mars 2020 rover. We're landing in an ancient river and lake system where we believe would have conditions suitable for microbial life in the distant past, millions of years ago. We're bringing back these rock samples with the hopes of studying them on Earth and answering the fundamental question, has there ever been life on Mars? And also, how has the Martian system, how has the planet itself formed? Understanding that question will help us understand how our own planet formed. So the other part of my time is working on understanding what it takes to eventually send humans to Mars. We've been working over the past several years trying to understand where water is distributed across Mars. On Mars, water doesn't exist as liquid as it does on Earth. It exists as ice in one of its forms, buried underneath the surface. And when we land humans, we want them to be able to access water because water can be used both for drinking, you can make oxygen out of it, and you can also convert it to rocket fuel. And so we've been trying to increase our understanding of where water is across Mars over the past several years with the goal of selecting a landing site where we'll eventually send humans to Mars. And once we select this landing site, we can start designing the logistics systems and understanding all of the other systems that are involved in ultimately supporting a human presence there.
So Sydney, we're going to dive deep into some of the lessons that NASA is extrapolating from some of the Earthbound logistics missions like Antarctica and also the missions back and forth between the International Space Station and Earth. But before we do that, I want you to give our Freight audience a little bit detail on the complex trip that the Mars Perseverance took from your labs there in California to the Kennedy Space Center in Florida before now being just months away from being to Mars. Tell us a little bit about that trip that it took.
Yeah, sure. So the Perseverance rover consists of 7 to 8 different instruments built from laboratories distributed across the world. And so that is assembled in a clean room in Pasadena, California. It needs to be a clean room because you don't want any dust particles to get on your instruments, because once it gets to Mars, you can't clean your camera lens, for instance, right? It also needs to be protected from getting Earth microbial matter on the rover, because if we land on Mars and we take some measurements and we find something like methane, which is a sign of life on Mars, we don't want that methane to have come from Earth. We want it to be pure Martian indigenous stuff. And so to pack it up and send it to the launch pad, we need to put it into a massive crate. It's climate controlled. It's got positive pressure in there, so it blows all of the air out to maintain that clean, dust-free environment. We send it to March Air Force Base, which is local to us. It's put on the back of a truck, driven there, and then loaded onto these military aircraft, these C-17s and C-5s, and they're flown all the way from California to Florida to our launch site at Kennedy Space Center. Before it gets put on top of the rocket, it's actually assembled for the final time and tested at the launch site, again within a climate-controlled facility. And then it's all folded up so that it can fit into the nose cone of the rocket. And then that nose cone is stacked on top of the rocket. And then come launch day, we light that candle and send it off. It's on its way to Mars.
I like that. Light the candle, send it to Mars. Let's talk about some of the lessons that NASA is extracting from Earth logistics missions, notably Antarctica and the International Space Station. Before we get to that, there's 3 things that you wrote in your paper that you published last year that have allowed for us to have continuous human presence on both the ISS and the South Pole. Can you tell me what those 3 things are?
Yeah, so the first one is multiple ways of getting stuff to your final location. So we call it multimodal logistics systems. You have for example, in Antarctica, you have large ships that send cargo that is not time sensitive to Antarctica, whereas when you send crew, it's by aircraft. They take a plane from California to New Zealand, and then from New Zealand, they go to the coast of Antarctica, and from there, they fly to the South Pole. Same thing with the International Space Station. We have launch sites that send cargo to the International Space Station distributed across the planet at different locations. And then we also have different ways of getting astronauts up to the space station. So for the last few years, we relied on the Russians to launch humans from Kazakhstan to the International Space Station. But more recently, you may have heard of the launches with the SpaceX crew capsule. The last one that just happened a few weeks ago, launched from Florida. So that's another vector. Prior to that, we had the space shuttle, and in the future, we'll have Boeing, another commercial provider, sending crew to the International Space Station. So that's one of the key lessons, multimodal logistics. The other one is having generous stores of contingency supplies. So with many of those locations, they're very difficult to access. In Antarctica, for instance, you can only actually get people and crew in and out for about a 2 to 3 month period per year. In other times, it just gets too cold. You can't fly in because the temperature is so cold that your fuel becomes a gelatinous fluid, and aircraft engines don't like jelly-like fuel flowing through them. And you can't use ships because the ice becomes too hard. And so because you can't access these areas frequently, you need to have lots of supplies of food, water, spare parts to keep you going until your next resupply opportunity. And so that was done in Antarctica. We do also do that on the International Space Station. We have lots of supplies of water to produce breathing oxygen and also drinking water for the crew available on board. And the final one is that we use local resources where available. So in Antarctica, they use water from ice. So they actually melt the local ice and turn that into water for drinking. And in the space station, we rely on the vacuum of space, actually, to create a pressure difference for us to use our life support systems to clean air, for example, to scrub the air from CO2. So those are the three main lessons: multimodal logistics, general stores of contingency supplies, and then exploiting your locally available resources.
So you mentioned one there, that there's only a short window for us to get supplies in and out of Antarctica. That's one of the reasons that you guys have looked to Antarctica for lessons.
Yeah.
Tell me some other reasons. Why is Antarctica so important to learning lessons to eventually get us to Mars?
Yeah, so when you think about Mars, it's a cold, dry desert, and that's exactly what Antarctica is. Mars, you can only get to Mars once every 2 years. You have to wait for Earth and Mars to align in their orbits around the sun, so that you can send something to Mars in a fuel-efficient manner. That's similar to Antarctica. You can only get into Antarctica for 2 or 3 months per year, and then you just have to stay there for a long period of time before you can get more supplies. So the reason why we've been starting to look at Antarctica is because environmentally it's the same thing, and also in terms of how you have to think about logistics and keeping a crew of people alive there over a prolonged period of time is similar, in that you have this big rush to get all your cargo out there to keep the crew alive, and then they're basically on a self-sustainment mode for several months. For Mars, it's 2 years until you get your next resupply. And so the strategies they've been looking at in Antarctica, we've been starting to study them closely and trying to understand what we can apply to Mars.
All right, so let's talk about that self-sustainment mode. I see two distinct points that are worth talking about here, and that's water and waste. So you mentioned water there to begin with, but and we know that one of the deciding factors of where we land on Mars is water availability. What lessons have we learned from Antarctica that have guided our search or changed our understanding of the water needs on Mars?
Yeah, so in Antarctica, ever since the 60s, they've been using a technology called the rod well, which is basically you put a hot heating element on a fishing line, you drill a hole, and then you put that heating element underneath the subsurface, and that melts the ice, and then you pump that up to the surface and recover that. That same technology is actually what we're starting to think about employing on Mars. And so if you're using that technology, you need to have the same kind of feedstocks, which is subsurface ice. And that's why we've been starting to focus on looking for subsurface ice across the subsurface of Mars, using our fleet of satellites that are orbiting Mars.
All right, Cindy, let's talk about waste for a moment. It's due to different reasons. There on Antarctica, it's due to international treaty that they have to reduce waste and minimize their carbon footprints as much as they can. But that's going to be the same deal when you guys are in Mars. They're going to have to reduce waste at any point. So what lessons have we learned about waste in Antarctica?
Yeah, so waste is a really interesting question. So in Antarctica, all of your human metabolic waste, so whatever you flush down the toilet, actually gets processed locally. So none of that bacterial matter that comes from our bodies can contaminate the pristine environment that is Antarctica. And that's there because of the International Antarctic Treaty. You can think of Mars as being the same thing. It's a pristine nature preserve, if you will. We want to keep Mars itself as clean as possible when we get there, so that whatever science and exploration we do is of the Martian environment rather than of our own bacterial waste. And so you can imagine that on Mars, we're going to have to start thinking about how to process any of that biological waste that we produce. This is an open question that we haven't really thought about. There's also just general packaging and trash waste. So in Antarctica, they compress it and they fly it out. They ship it back to California where it gets processed. You can't really do that on Mars. Launching things from the surface of Mars and sending them back to Earth, very expensive endeavor. So we're going to have to start thinking about how you process that waste. There have been NASA projects looking at incinerating that waste and turning that into methane and other gases and fuels and consumables that you might be able to use. There are other options looking at if it's plastic or metal, for example, can you melt it down into a feedstock for 3D printing new parts? So these are still very open research questions. We're at the very early stages of exploring this. But some of those waste problems of dealing within this pristine environment and generating waste, and how do you manage that? There are very open questions that we're looking at.
So how do they do it on the ISS? I remember you mentioned something about kind of just blasting it into the Earth's atmosphere.
Yeah.
So that's not going to really, how do they do it on the ISS?
So the ISS, it's a simple, elegant solution. They basically, whenever you have a vehicle resupplying cargo from Earth, they stockpile all their trash on the ISS. You can imagine it's a home that you can't go outside of easily. And you don't want to throw your trash out the door because it becomes a satellite that could come back and crash into you and create a hole in your home. And so on the ISS, they load up the resupply vehicles with all their trash. And those resupply vehicles, once they eject from the ISS and return to Earth, they just burn up in the Earth's atmosphere on re-entry. So we're essentially just burning up our trash by dumping it into the Earth's atmosphere at the ISS. That's not something we can do on Mars as easily because we'd have to launch it up. So looking at options for processing it on the ground is an open question that we're looking at.
All right, Sydney, let's stay with the ISS for a moment. Let's talk about some of the things that we've learned that humans need in space that we didn't know when the ISS was first launched. What has had to be added to the ISS since it was launched in the early 2000s?
Yeah, so one of the big lessons we've learned is the need for storage space, for spare parts. And, I mentioned earlier, we need generous stores of contingency supplies, especially as you have to self-sustain yourself for a longer period of time between getting a stockpile of supplies sent to you. And so initially, there was an issue with storing all the spare parts needed for the equipment. We actually didn't understand how much maintenance, especially our life support systems needed. You can think of, pumps and valves, systems like that, where you test them on Earth, they behave one way, but then you take gravity away from it and you're in the International Space Station and different things happen. And so what we've had to do is actually redesign some of those systems and then launch new versions and keep spare parts on orbit to keep the existing systems running, to keep the astronaut crew alive. And so you can imagine how much space that takes for storage. And so towards the end of construction of the International Space Station, one of the last missions that the space shuttle launched was essentially a used shipping container for space. We called them multi-purpose logistics modules. We used to load them with cargo and send them to the International Space Station. But essentially, it's a shipping container, and then we docked that to the space station, and that serves as our in-space storage closet. We had to increase the amount of storage that we needed for all those spare parts and those consumables like water and food that was needed to support longer durations of larger crews on the International Space Station.
And Sydney, the ISS is huge. For those in the audience that don't understand how big it is, it's 350 plus feet wide, and it's more or less a huge storage unit in a lot of cases. There is a lot of stuff up there. It's more or less a big warehouse. I think it would be interesting to hear you explain a little bit about how things are organized and how things have had to be become more organized as we've been up there longer.
Yeah, definitely. So, say you're an astronaut and you're doing a maintenance job on the toilet, the space toilet, and you need a special tool like a wrench, and you're replacing the pump. So the pump would be stored in a bag, and that would be stored on a shelf within a module somewhere in the space station. And in space, because it's weightless, you can store things on the floor, on the ceiling, on the walls. Things float around, and you have to tether it. And so that pump might be stored in one bag, and then the wrench might be stored somewhere else. And before we had that space closet that I mentioned, things were a little less organized because we didn't have as much room, and astronauts were just cramming cargo wherever they was convenient for them. And so at one point in time, astronauts were spending up to 2 hours a day looking for parts and components to do their jobs. And you can imagine how that's really not a good use of time in space, looking for stuff. And so more recently, we've been experimenting with using RFID technologies, tagging everything so that we can track exactly, which module and which bag an item is in to save that time. We'll definitely be employing those types of systems when we send crews out to Mars on the journey to, and definitely on the surface of Mars as well.
So Sydney, let's talk about some of these supplies that each crew member aboard the ISS needs and what we expect those needs to be for Mars-bound missions. So I read that about 1.5 metric tons of supplies is needed per astronaut per 6-month stay. And you told me offline that the goal eventually is to become efficient enough that we can bring that number down below 1.5 metric tons per person per 6 months. Tell us a little bit about how what the goals are to reduce that, and how the landing site that we eventually choose will determine how much supplies we need to bring up.
Sure. So what drives your logistics demand is really driven by your landing site and how long you're going to stay there for. So say you're out on Mars, there are three main ways to get stuff to you. You either carry it along with you, or you mine it from something locally, right, and process it. So for example, water and oxygen, as I mentioned before. Or you recycle from your existing waste streams, or cannibalize old parts. So you're reusing and recycling. So those are the three main ways, right? You're delivering from Earth, you're using something locally, or you're repurposing something that you already have with you. On Mars, because the distances are so far, you can only get stuff to Mars once every 2 years. We've been trying to find ways to minimize the amount of cargo that you would need to send from Earth. We're looking at increasing the self-sustainability of astronauts on the Martian surface. And so the landing site, I mentioned earlier, we've been mapping water because that's a really useful local resource that could be used. The landing site that we ultimately choose would ideally have vast amounts of subsurface ice, which we could process into water. Once you have water, you can produce oxygen for breathing. You have water for drinking. You can also crack that and combine that with the Martian atmosphere to create a rocket fuel. And you're starting to have a local resource economy that you can bootstrap yourself on and build upon yourself. With these systems, as we've learned on the International Space Station, these processing systems, you might need spare parts. And that might be a while until we can build them locally. So there will be some level of supplies required from Earth. The goal at the moment is to try to reduce that by trying to leverage whatever we can locally, either in terms of resources or coming up with approaches or techniques or technologies that can recycle waste streams so that you can use them again and replace some of that cargo that you might need to send from Earth in the first place.
Okay, Sydney, I hate to say this, but we're running out of time here, but I do want to get the one question that I'm sure is on everybody's mind. We've gone through this whole conversation and we haven't talked timeline at all. We don't know exactly when these missions are projected. Tell us, what is the ideal timeline? When can we expect or hope that the Mars sample return mission could launch? And then, what will be needed in between then and the next launch that will eventually carry humans at some point decades away? When can we expect that to get going?
Yeah, so we're aiming to launch Mars sample return in 2026. Launching from the surface of Mars to bring those rock samples back to Earth in 2029, and they'll get back to Earth in 2031. So Mars sample return is really important. Not only does it give us those rock samples to study the history of Mars, we can also learn about the properties of the Martian soil in the labs, and that affects how you design the systems to keep humans alive. So for example, seals, you don't want them to be contaminated with dust, for instance. It also is a demonstration for a round-trip mission from the surface of Mars. This will be the first time we'll ever launch something from the surface of Mars and bring that back home. You can imagine that being a really important capability for when we send humans to Mars, because we want to send them back home. So you can think of the rock samples as, mini astronauts coming back to Earth. So beyond Mars sample return, we're exploring potentially sending a mission out to better map water distribution across Mars. It's in the preliminary formulation phase at the moment. It's called Mars Ice Mapper. And the goal of that mission is to refine our understanding of where ice is distributed across Mars. The idea is that based on the outcome of that mission, we'll have sufficient information to be able to narrow down and select where we want to send humans to Mars. And so when we ultimately send humans to Mars, we're looking at the late 2030s timeframe. It will likely initially be missions where humans will orbit Mars and then come back, and then eventually will transition into landing on the surface of Mars, for short periods of time and then progressively expanding the length of time that they're spending on the surface of Mars.
Sydney, we got some exciting years ahead of us, my man. I'm glad to have someone like you on the mission board taking care of things. Thank you again so much for taking your time out of your day, man. This is very important to us, and we really thank you for it.
Excellent. Yeah, thanks for having me. Excited to talk about it. And yeah, anytime. Love to be back on again.
Great, man. We'll definitely have you back. This has been awesome. And everybody else, you stay tuned. We've got a lot going on the rest of the day. You guys stay tuned and enjoy.